Hi everyone, welcome to your lesson on beta radiation. Last time we saw about alpha particle radiation, today we're going to learn about a different type of radiation called beta radiation. So the goal is to understand the process of beta radiation. And in some ways it looks very similar to alpha particle radiation, and in other ways it's different. So one of the ways in which alpha radiation and beta radiation are similar is that they come from inside the nucleus. So we saw that alpha particles were just, a chunk of protons and neutrons that were ejected from the nucleus. A beta particle is similar, but instead of being two protons, two neutrons, it's actually just an electron. So it's an electron that came from the nucleus. Now, that should cause you to sort of scratch your head a little bit and say, wait a minute, that doesn't make sense. Because what you've learned all year in chemistry is that that electrons orbit the nucleus. Electrons are found outside the nucleus, protons and neutrons are found inside the nucleus. So how is it possible that an electron can come from the nucleus when there are no electrons there? And the answer has to do with neutrons. So you're used to thinking of neutrons as a solid sphere that have a mass of 1 and have no charge. So I am sort of coloring in green on my diagram what I'm calling the neutrons. Okay, and the black particles in the middle would represent the protons. Okay? And you can see here that this beta particle, the arrow is showing that it came from a neutron. So what's going on there? So again, I've told you that neutrons are these particles with a mass of 1 and no charge. Now here's the thing. That's sort of true, but not entirely. A neutron is a big particle. It's not that it has no charge, it's that it has both a positive charge and a negative charge. So a neutron is neutral, but it's neutral because it has both a positive charge and a negative charge. When you put the positive charge and the negative charge together, they cancel each other out, so we sort of ignore them. So I want you to think of a neutron as actually being a proton and an electron living together. So the proton has the positive charge, the electron has the negative charge, and the mass goes with the proton. Because we've already talked about how protons and neutrons have the same mass pretty much, and electrons are so small by comparison we sort of ignore their mass. So when we talk about a neutron, a proton, and an electron, it's really that a neutron is sort of a proton and an electron squished together, living together. And so when we talk about beta particle radiation, in this idea of electrons that come from inside the nucleus, what we're really talking about is electrons that came from inside a neutron. So in beta particle radiation, we have electrons that are being ejected from a neutron inside the nucleus. So pretend for a moment, for example, that this neutron ejected this electron. So if this neutron ejected this electron, what you're left with after that is the positive charge and pretty much all the mass. So essentially, you're left with a proton. And that's what happens during beta particle radiation. You have a neutron that ejects a beta particle, and when it does that, the neutron itself turns into a proton. And I've got a sort of cute little cartoon of that down here. We start with a neutron. The neutron has 0 charge, right? It's neutral. But then all of a sudden, it's going to burp out. That's the vocabulary they're using here. It's going to burp out an electron, right? And that electron is a beta particle, because a beta particle is just the name we give an electron that came from inside the nucleus. And what we're left with at that point, after we get rid of the negative charge, we're left with mass and we're left with a positive charge. So we're left with a proton. And the same idea is written down here. The neutron emits an electron, and when it does that, it changes into a proton. So now with all that information, we need to take that and apply it to a radioactive decay problem, just like we did with alpha particles. So here I have the element mercury, Hg, with atomic number 80 and atomic mass 201. So if I pretend that one of the neutrons living inside the nucleus of mercury is going to eject a beta particle, I know that that neutron will then turn into a proton, which means that unlike with alpha particle radiation, the atomic number actually goes up. And it goes up because I created a new proton. So I started with the element mercury and atomic number 80, but the element I produce is going to have the atomic number 81. Now, in terms of mass, we know that the mass of mercury was 201, which means it had a total of 201 protons and neutrons. That stays exactly the same. And the reason for that is the total number of particles inside the nucleus doesn't change. I lost a neutron, but I gained a proton. So that evens out. So if I started with 80 protons, now I have 81, but I have one fewer neutrons than I did before because one of the neutrons changed its identity. So the total number of particles inside the nucleus stays the same. So to figure out what this new atom is, I need to go to the periodic table and figure out what element has atomic number 81. And the answer is an element called thallium, which is Tl. Now I'm almost done. So just like with alpha particle decay, I now need to show that not only did I create thallium, but I also let off a beta particle. So to represent a beta particle, I just draw the symbol beta. A beta particle, just like an electron, has no mass. It's virtually weightless. So we give it mass number 0. And because it doesn't have any protons, it only has an electron, we actually say that its atomic number is -1. So that's how I would write this nuclear decay reaction. So here's a second problem. Pause the video and see if you can do it on your own first, and then listen to my explanation. So we have polonium with 84 protons and a total mass of 209. Polonium is going to undergo beta decay, which means one neutron inside that nucleus is going to turn into a proton. So if a nucleus turns into a proton, if one neutron in the nucleus turns into a proton, the number of protons actually goes up by 1, which means my new element is an element with atomic number 85. The mass number stays the same because the total number of protons and neutrons in the nucleus hasn't changed. So now I need to go to my periodic table, look up element number 85, and I find AT. So that's the daughter element that's produced when polonium undergoes beta decay. That's how I would phrase it. I would say that when polonium undergoes beta decay, we produce AT with atomic number 85 and atomic mass 209. And to finish this off, I have to add the beta particle. So plus a beta with a mass of 0 and an atomic number of -1. So quick recap on today's lesson. The goal is to understand the process of beta radiation. You learned that a beta particle is similar to an alpha particle in that it's a type of radiation that comes from inside the nucleus. But other than that, it's fairly different because it's much smaller and it has a negative charge. So we talked about how it's strange to think of an electron inside the nucleus because electrons live outside the nucleus. And then I showed you how actually that electron, that beta particle is coming from inside of a neutron, because a neutron is really just a proton and an electron smushed together. When that neutron gives off the beta particle, it turns into a proton. And then we apply all of that information to write nuclear decay reactions.